Hello, thank you. When I saw the schedule first, I wasn't sure if that was out-of-the-box thing as a compliment, but I hope it is now. Anyway, so I'm Siddharth Krishna. I'm going to be telling you a little bit about a new abstraction for verifying concurrent data structures. This is joint work with Dennis Shasha and my advisor, Thomas Wies, and we're all at NYU. So I'm going to start off with an example of a data structure to motivate the problem that we're looking at. And this is going to be a non-blocking concurrent implementation of a mathematical set, which is implemented as a sorted list. So I'm just going to show you what the algorithm does just by means of animation and examples. So here we have a state where the set contains the integers 1, 3, 6, 7, and 9. And this big red thing over here is a thread that wants to remove the element 7 from the set. So as you would expect, it starts at the head of the list and it walks down the list. Once it finds the element 7, in the sequential case, what you expect it to do is simply swing the pointer 6 from 7 over to 9. This unlinks the element 7 from the list and therefore also from the set. But this is not okay in the concurrent setting because there may be another thread, like the blue thread over here, that's sleeping on the node 7. And say the blue thread was about to insert the element 8 right after 7. When it wakes up, it would not know that 7 is no longer part of the list, right? So the solution of Harris in this concurrent setting, I mean, of course, you could solve this with locks, but to do it in a non-blocking way, the solution is that the red thread atomically marks this node 7 as being logically deleted, which I denote by changing the color to red. And now when the blue thread, when the blue thread wakes up, it knows that 7 may not anymore be reachable from the head of the list. So it gives up, goes back to the beginning, and tries again. So that's quite a simple idea. But notice that the red thread still cannot free or deallocate the node 7, because again, there may be a blue thread or another thread that has a reference to this node. If it wakes up and tries to go to the reference, it's going to be a memory error. So the solution here is to basically have a second list, which is the free list, a list of red nodes at the bottom here. And what the red thread does is after it's set the mark bit to be deleted, it adds the node 7 to the free list and then swings the pointer to remove it from the main list. All right, so of course, this kind of moving the nodes from the main list to the free list may also move threads from the main list to the free list, which are sleeping. So you may have a thread that wakes up, finds itself now in the free list. But the beauty of this algorithm is that this thread doesn't have to do anything special. It simply just follows the blue pointers and it leads back to the main list. So notice that when you move the nodes over to the free list, you don't change the blue pointers. So this thread just walks back up. Once it's in the main list, it can continue and go and find whatever node it wanted to. So the elements are still in sorted order. Okay, so that's the data structure that I want to verify. And you may look at this picture and you may say, all right, that seems reasonably simple. I mean, what's the big problem? And to tell you that, I'm going to give you like the world's shortest introduction to separation logic and inductive predicates. So in separation logic, it's a logic to describe data structures in the heap. And here is like an example of how I would describe a simple singly linked list. So the definition on the top is an inductive definition or inductive predicate that says that a list is either empty, a list segment is either empty if the endpoints are equal, or there is at least a single element x that points to some z, and there's a list segment from z to the other endpoint y, right? And this describes a list like you see over here in the picture. I don't have much time to explain all the semantics, but sort of the key properties of this definition are the two following lemmas, which say that if I have a list segment and the endpoints are not equal, then I can unfold the list segment and get the head element and the rest of the list. And similarly, if I have a list segment and an element that points to the head of the list segment, I can fold the definition together and get back the list, right? And using these kind of rules, you can verify properties of programs that manipulate list segments like append, concat, all these normal things. And it's great. You can do a lot of cool things in separation logic. The limitations of these inductive predicates are essentially because of the fact that the semantics of separating conjunction and separating logic do not allow you to describe a node more than once. So basically this means that the heap graph I have here on the left is not described with the separation logic formula, list segment x to null star list segment y to null, because although I didn't tell you, the separating conjunction, the semantics of the conjunction say that the left-hand side and the right-hand side describe disjoint sections of memory. And you notice on the left, both these lists are not disjoint since they share this node at the bottom. What this means is that if I have a state of the Harris list and I wanted to describe this as a blue list star a red list, this is no longer true in cases where nodes have been added to the free list but not yet removed from the main list, because these nodes like 3 and 7 are shared between both the lists. So that kind of a naive approach is not going to work. Another feature of the Harris list that makes it hard to describe with inductive predicates is that these nodes like 6 can be pointed to from multiple nodes. They're shared by multiple nodes, which means that, and of course, an arbitrary number of nodes as you delete more and more elements, which means that you don't know at which point in the unrolling do you describe this node 6. And the final feature of the Harris list that makes it difficult to describe is that threads, as I said, wake up in the free list and just walk down the blue pointers to the main list, and they enter the main list at arbitrary points in the middle. If you remember from the list segment lemmas, inductive predicates can be unfolded only in one direction, right? So list segments can be unrolled only from the head. But here you might have to describe the state of the blue thread at this point, you may have to unroll the structure at some arbitrary point in the middle, which is also hard to do. So of course, this problem has been studied before, and there's a lot of really cool work to tackle these issues. I'm just going to cover this approach because it's very related to our approach. And the idea here is to use this new operator, which is an iterated separating star, which basically says that I have a set of nodes capital X, and for every node, a particular local condition phi of X holds. This is great, and it's really easy to reason about arbitrary traversals because you can just pick out any node from this bag, and you know what it looks like. But you can't encode inductive properties like reachability in this format. So I couldn't say, for instance, all the nodes are reachable from one of these two heads. So I can't tell the previous picture from this picture, and this is bad because I can't guarantee the absence of memory leaks. Okay, so what's the problem? The problem that we're trying to solve is, can we have an abstraction mechanism that can handle features of data structures such as the ones I've shown you before? And the key idea is that the approaches I've shown you sort of lie on a spectrum. One end, we have inductive predicates, which are great for inductive properties, but not so good if you have arbitrary traversals and all the other features I've shown you. On the other hand, you have iterated separating conjunction, which is really easy to reason about, but it can only talk about local properties. Wouldn't it be awesome if we could do both? Yes, you can, if you take your inductive properties and you write them as local conditions. That's not possible in general, so we allow the local conditions to depend additionally on a single particular kind of inductive quantity that we call the flow. So, example of a flow. Supposing I had this graph that I showed you over here, and the property I want to describe is that all the nodes that are reachable from the root node form a tree. Can I write this in terms of a local quantity? Yes, if I had access to the number of paths from the root at every node. If I had that quantity at every node, then I could say this property by saying every node has at most one path from the root. Right? So sort of informally, we assume that our memory states are graphs of a finite set of nodes with edge labels, and the edges are labeled from a domain which is called the flow domain that I'll get into later. Here it's natural numbers, and I label all the edges with ones, and all the edges that are not present, those get labeled zeros. So the flow is computed by this equation, which starts off with an inflow, which is like an initial estimate, right? So if I want to count paths, my initial estimate is that root has one path to itself, and every other node has 0 paths. And I start with the flow equal to this inflow, and I iterate the following equation until I reach a fixed point. This basically just says that every node, for instance, this node over here, is going to get the value 0 plus 0 times 1 plus 1 times 1, so it's going to get 1. As I iterate this forward, when I reach a fixed point, I basically get that the flow at every node is equal to the inflow plus the sum of the flow of every other node times the edge labels coming in. And in terms of numbers, this is basically saying the number of paths to a node is the sum of the number of paths of all the predecessors. So because I encode my edge labels in this way, I get that this flow quantity is computing the paths. If I have the number of paths at every node, I can now express properties of data structures. I can say something is a tree by saying every node has exactly one path from the root. I can also talk about other properties that are local to nodes, for instance, the number of outgoing edges. So I could say that a data structure is a list by saying that it has exactly one path from the root and at most one edge that leaves it. Okay, so I can show you how to describe lists and trees, but you could already do that. What do you get new here? The point is that the flow equation that I've shown you here, the plus and the dot were addition and multiplication of natural numbers, but that does not have to be so. We use natural numbers and addition and multiplication, but in general, we can use any ordered semi-ring with a couple of other properties. So for instance, we could also use integers with minimum and maximum as my addition and multiplication. Now the same equation on the top computes, instead of a number of paths, it computes sort of the maximum value on some path from the root to that node. And there are many other examples in our paper. But you're like, okay, what is this quantity? Like, how does this help me say anything? The beauty is that if I take the product domain of two flow domains and compute the flow on this product domain, I get the product of the flows on each domain. So now by taking the product of these two domains, I can both say that something is a list using the path count, and now there's only one path from the root. I can say that this path is sorted. So I can say something is a sorted list. Or similarly, like I could say min heap and a whole bunch of other properties. So coming back to my example, I can now describe the Harris list by just saying, I take the product of two path counting flows from each of these heads, and I just say that every node has either one path from the main head, or one path from the free head, or one path from both. So I don't have to worry about the whole overlays and so on. So flows are pretty expressive. We can describe a whole bunch of common data structures and a whole bunch of data structures that are hard, like overlaid, irregular, and unbounded sharing. Industrial predicates are still simpler in some cases, of course. So quick second part of my talk is, now that we know how to express a whole bunch of properties using flows, how do we reason about programs that modify the graphs and preserve these flow properties? And to tell you what the challenges are, I'm just going to give you a really simple but contrived example. Supposing my invariant that I wanted to maintain was that every node had at most two paths from the root. So this graph here satisfies the invariant. And my program was going to take this pointer and swing it to this pointer as shown. So clearly, if you look at it, you can say, okay, the invariant is still maintained. But what we want to do is reason compositionally. So we assume that our program only has access to these three blue nodes that I've shown here. Now the question is, if I'm only looking at these blue nodes and the pointer gets swung, firstly, how do I calculate the new flow inside the blue graph? Because that could have changed, and here certainly it has, without looking at the red graph. So I want to calculate the new flow in the blue graph, only look at the blue graph. And secondly, changing edges in the blue graph could change the flow in the red graph as well. So how do I make sure that the invariant is preserved by the new flow in the red graph? These are the two questions. So the solution to the first one is quite simple. We use the initial estimate inflow that I showed you a couple of slides ago. So what we do is that when we split a graph into two subgraphs, we define the composition operator such that the inflow of the subgraph is of this form shown here on the bottom. But basically what it does is the inflow captures the number of paths that come from the red subgraph. So here it's 1 because there's one path coming from the red subgraph, even though there's another path coming from here, from the left. But the second path comes from the blue subgraph, so I don't have to keep track of it. That's captured by this one over here. So the theorem in our paper says that if I decompose graphs this way, then the flow I compute in the subgraph is going to be the same as the flow computed in the larger graph. So this helps me to, after a modification, compute the new flow in my blue graph and show that my invariance is still maintained. As a side note, this composition operator satisfies the conditions needed to be a separation algebra, which means that we can use it as a semantic model for separation logic. The second problem was, what do we do when we modify the graph, right? What about G2? Well, as you see in this example, the modification is okay because the number of paths to this node is still 2, right? So you might think, let's just preserve the number of paths going to every node in the second subgraph. Well, something like that works. I don't have time to go into the details. But the key insight that works is that all I need to do is look at every source node in the blue graph, which are these two nodes, a node that gets at least one path coming in, and preserves the number of paths between this source node and every destination node in the other subgraph. Sort of like, it's not just important to give you the same amount of paths coming out, but also which source did the path come through. So this extra information. So this is called a flow map, and together the inflow and the flow map form what we call a flow interface. And you can think about the flow interface as like sort of a relay guarantee of this subgraph with respect to its context graph. The inflow says this subgraph expects so many paths coming in at these nodes, and the flow map says if you give me a path at these source nodes, then I will give you a path at all these destination nodes. And another theorem in our paper is that if you modify a subgraph with another graph that satisfies the same flow interface, then the composition is still going to be okay, and the flow at all the rest of the graphs is going to be the same value, therefore the invariants are going to be preserved. Great, so to quickly recap, if you want to use flow interfaces to prove a program, you need to first pick a flow domain. Like I said, you can use product constructions and so on, express your invariants in terms of the flow at local nodes, and then look at your program and show that every modified region satisfies the same flow interface, thereby maintaining all the flow invariants. This looks really simple. It's not. There are also some other interesting questions and some more tricky technical details. It's all in the paper. finally, I just want to mention, well, of course, we verified the Harris list in detail in our paper, but another application we have that I think is interesting is we took a paper from a long, long time ago that had a template algorithm for constructing concurrent dictionaries. And this template algorithm was given in terms of these invariants that was very global, but those invariants implied linearizability of the algorithms. So what we did is we took these invariants, encoded them using flows, and put the whole flow machinery inside concurrent separation logic, RGSep, and we proved memory safety and linearizability of the template algorithms for dictionaries. This is pretty cool because A, we could prove it without just like agnostic of the implementation, and B, we also instantiated the template and got a pretty simple proof for the concurrent B+ tree, which is so far has been pretty hard to prove correct. And of course, a mandatory slide to show you that my proofs are not so horrible and they fit in a slide. The other thing I want to highlight here is the reasoning about the interference between threads. Normally, this is quite complicated because it depends on all the sort of different protocols that threads interact by. But because of the fact that we could hide away, sort of abstract from the implementation, we were able to get away with just 3 sort of actions that describe how threads interact. So to conclude, I've skipped a lot of details, but sort of the high-level idea is that we have a new data structure abstraction. It's a new way of describing data structure properties. That's especially useful if you have sharing, overlays, and other features that you see in concurrent data structures. Things that I didn't really get into is that it treats data and structural properties uniformly, so you can stack them on one another. It remains within separation logic theory, so you can use your favorite separation logic with flow interfaces. Yeah, thank you for your attention, and happy to take your questions. Yes, actually we can. So I've spread through the slide, but I think it was on the slide. Oh, but yeah, the answer is yes. We can use it for both balanced and AVL trees and a whole bunch of other data structures.
All right, very nice talk and very elegant idea. I'm curious how the flow abstraction relates to abstractions by means of ghost state that have been used to reason compositional graph algorithms, most notably in the works by Aquinas Hobor and Alex Danevsky.
Yeah, it's a great question, and we were quite inspired by some of that work as well. I think the relation is that you could think about the flow graph as a ghost state, especially the inflow is basically a ghost state that comes in. But I think some of the key differences are that we tie the ghost state in a more fine-grained manner to the real heap. So when we sort of look at the region that's modified, we're only considering the ghost state in that region, in a sense. Like I think I might be mistaken, but I think there you're looking at the graph both as a mathematical graph and as a concrete heap, as a bag of nodes.
That's right.
But here there's slightly more sort of fine-grained linking. Happy to go into the details later as well.
And that gives you more modular reasoning, or what's the advantage?
A little more compositional reasoning, and for instance, there some of the updates rules were proved as mathematical lemmas in the paper, whereas here the update is sort of baked into the interface preserving theorem. It's called like a replacement theorem. So some of the update reasoning is part of the logic as opposed to a lemma that we prove about the mathematical ghost state. But yeah, it's a great question.
Take a plan.
So one of the nice things about separation logic is you get sort of these nice algebraic kind of properties. So, you know, for example, a list segment plus a list segment gives you a list segment. So you get these nice compositions and decompositions. So is that, I guess that you can see that some of these kind of compositions and decompositions seem obvious to me, but is there still that kind of flexibility in this approach? Do you still get those kind of identities?
Yeah, definitely. I didn't have time to go into it, but with the flow interfaces, when you build a separation logic out of it, you can define these graph predicates that have these data structure agnostic composition and decomposition lemmas. So you can do sort of similar things here, like splitting a graph into a node and another graph, or putting 2 graphs together to get a bigger graph. And the cool thing here is that these lemmas are true regardless of what your invariant on the local nodes are. So this is true whether this is describing a binary search tree or a list or something else.
Okay, so you can do things like kind of nest sort of a flow graph in a flow graph in a flow graph, and then sort of reasoning about that kind of nesting. I suppose that I'm just thinking about kind of shifting between sort of the sizes of the kind of flow graph you're considering.
That's a good. We haven't done that explicitly yet, but I don't see why not. Yeah, I think we should be able to nest flow graphs and flow graphs.
Okay, let's talk about this offline.
Yeah, definitely. Yeah.
Hi, have you looked at any kinds of algorithms with parent pointers, like the union find algorithm?
Not yet, but since our conversation yesterday, I wrote to Thomas, and we're going to look at that next. But I think, in theory, I don't see why it should be too hard, because again, different traversals can be stacked on top of each other. So the parent pointer is just simply going to be another product domain over whatever domain we use to describe the tree itself. But yeah, I think that's a great thing to look at. Thank you.
All right, very good. Thank you very much.
Thank you.